podcast is brought to you by LMU Munich.
First, I would like to thank the organizers for the opportunity to speak here. So, my goal would be to review some recent progress in quantum field theory, and I'll be emphasizing some general results about quantum field theory. And also, I want to say out loud that of course, the number of people who have contributed to this subject is far greater than the number of people I could ever hope to acknowledge here. So I apologize in advance if I've missed any references. So just as an overview, the kind of questions that I'm going to discuss, there will be a few topics that I would like to cover. And the kind of questions that I would like to discuss are, for example, given some quantum field theory, does it break a global symmetry? And I'll show you that in some circumstances, you can prove that the symmetry is broken or prove that the symmetry is unbroken. So that's one line of questions that you could ask. We will also discuss briefly the question of whether the renormalization group flow is reversible or not. Also, I'll mention a few comments about the question of whether scale invariant theories are conformal. I'll just mention a few comments because they feature in some of the discussion. And finally, I'll discuss a somewhat unrelated subject that is still in progress about operator bounds in unitary conformal field theories. So the spectrum of operators in scale invariant models in 2+1 dimensions or 3+1 dimensions. So most of these questions have a clear-cut answer in 2 dimensions. So for example, I'll just review quickly. It's very well known that in 2 dimensions, theories cannot break global symmetries. That's the Coleman theorem. It's also very well known from Zamolodchikov's work that in 2 dimensions, renormalization group flows are irreversible. Another thing that is known due to Polchinski from the 80s is that theories that enjoy scale invariance in 2 dimensions in fact enjoy the whole conformal group. And finally, there are many results about operator dimensions. Operator dimensions, the spectral problem in 2 dimensions has a lot of interesting results due to the Virasoro symmetry and so on. However, in higher dimensions, many of these questions, which are obviously very basic questions in quantum field theory, they still stand open. For example, in more than 2 dimensions, we don't yet know whether a consistent unitary theory that enjoys scale invariance is necessarily also a conformal field theory. So a conformal field theory would mean that there is more symmetry, not just scale transformations. And of course, this problem is at the heart of, is really fundamental and for many fields of physics, not just high energy physics, but also for condensed matter physics, statistical physics, and so on. And so we don't yet know the answer to this question, even though there were many recent papers about the subject, but in fact, some of them are not compatible with each other. So I'll mention some more remarks about that. So I'll just review the problem of scale versus conformal, not because I have a solution for that, but because it will be important for some things that I'm going to say later. So a theory which is scale invariant is basically defined to be a theory where the trace of the stress tensor is a total derivative. So if the stress of the energy momentum tensor is a total derivative, then the theory is scale invariant. For the theory to also enjoy the full conformal group, you need this object V to be a total derivative itself. So it's like a problem in cohomology. When T is the derivative of something, it's scale invariant, and when this thing is the derivative of some other operator, then the theory is fully conformal. In fact, you can make this whole discussion a bit more sharp, and that's not emphasized in the literature. For theories that are unitary, it's enough that this operator V is a derivative of a scalar. It does not have to be a derivative of a tensor. You don't need this tensor, it never appears. So, so far the only universally agreed upon example of a theory that is scale invariant but not conformal is a compact scalar in more than 2 dimensions. So a compact scalar has this energy momentum tensor, which is traceless, but then it's not invariant under the shift symmetry of the scalar. So it's not a legal operator in the theory. If you try to get rid of the offensive term, so that to reintroduce the shift symmetry into the problem, you run into an energy momentum tensor which is not traceless, and it's not even a derivative of something. So a compact scalar is pretty peculiar in that it's a scale invariant theory, but it does not even have a scale current. It only has a scale charge. It's not a conformal theory, it's scale invariant, but it does not even have a scale current. And that's something that will be important for in a few more slides. So just some small conclusions from this small analysis. The free gauge field in 3 dimensions, which is dual to a compact scalar, is not a conformal field theory, even though it doesn't have a scale in the Lagrangian. In fact, it doesn't even have a scale current. It's a scale invariant theory, but it does not even have a scale current. And that's responsible for some things that people have been finding over the last year in various computations. The same is true about anti-symmetric tensors in 4 dimensions. Okay, so that will be important for some things I say later, and now I want to make some comments about correlation functions of energy momentum tensors. That is based on some work with Stefan Tyson and Adam Schweber that is not yet published. So I'll just remind you quickly that if you investigate the 3-point function of the energy momentum tensor, just in a general conformal field theory in 4 dimensions, what you find is that there are anomalies, trace anomalies, and people call them the A and the C anomaly. These are the 2 anomalies that appear in 4 dimensions. And here I'm discussing only conformal field theories. I'll make some comments about what happens when the theory is not conformal. So this 3-point function in a conformal field theory gives rise to 2 anomalies, A and C. And that's something to keep in mind. So the object that we investigated is a 4-point function of the energy momentum tensor. So it's T, 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 T with a completely independent indices. Oh, sorry, except for the typo here. These indices are supposed to be completely independent. And we do not impose conformal invariance. So you could just investigate a 4-point function of the energy momentum tensor in any consistent unitary quantum field theory without imposing conformal invariance. So the classification of all the possible terms is pretty hard. There are many possible constructions just because of the kinematics. And it turns out that there are thousands of terms that you could write on the right-hand side. But there is one particularly interesting amplitude that appears in the decomposition of the 4-point function. And this amplitude we call B. So it's a function of the momenta, P, Q, and R. So there is one special amplitude, and I'll tell you what's special about this amplitude in a second. And this amplitude can be isolated by looking at the full expression for this 4-point function that we worked out. So this amplitude B that appears from this mess has 3 distinctive properties. One is that this amplitude survives when you take the momenta of the energy momentum tensors to be light-like. So even when you take P squared equals Q squared equals R squared equals 0, this amplitude still survives. That's one interesting thing about it. It also survives if you take traces over all the indices. So if you trace all the indices of all the energy momentum tensors, it still survives. Many other amplitudes die away, so they disappear when you take traces. And finally, when you take these traces and you go to the conformal limit, so you turn off all the mass parameters, this amplitude B becomes a pure number. And this pure number is A. Okay? So that's this is what defines this amplitude B. So that it coincides with A in conformal field theories, but it's well defined completely away from conformal field theories too, and it can be isolated by this algorithm. There are many amplitudes that satisfy the first 2 properties, namely they survive these kinematical projections, but they do not have anything to do with A in the conformal field theory, so they vanish when you take the conformal limit. So those amplitudes I'll refer to as B prime. So because those amplitudes B prime vanish in the conformal field theory, you can just use the Cauchy theorem and write formula like that the integral over these amplitudes B prime, it must be 0, just because it's some kind of Cauchy theorem, and these constants at infinity vanish. So we have a bunch of amplitudes whose integrals vanish, and there is one special amplitude B whose integral gives the difference between the A anomalies of the ultraviolet and infrared conformal field theory. Now, there is something interesting to say about these integrals. At least this integral, one could prove that it's positive. The way to prove it's positive, so there are many ways to prove that it's positive in Minkowski space. One simple intuitive way to prove that this is positive is by doing some Gedanken experiment where you couple the theory to some weak background gravitational field and you perform scattering of the conformal factor of the metric. So when you scatter the conformal factor of the metric, naturally you're sensitive to the trace of the energy momentum tensor. And I told you that this amplitude survives taking the trace. It's also natural to do this scattering when this background field is massless. And that's also something that this amplitude survives. So this amplitude survives the kinematical condition p squared equals q squared equals r squared equals 0. So all in all, from this Gedanken experiment that you scatter this particle phi, you learn that this amplitude has to be positive. And from that, there follows a simple inequality relating the anomalies of the conformal field theory that lives at short distances and the conformal field theory that lives at long distances. So every RG flow between conformal field theories that is unitary must be consistent with this inequality relating the anomalies of the two conformal field theories. Something that probably most of you are familiar with is the 't Hooft anomaly matching. The 't Hooft anomaly matching principle says that the anomalies of the UV and the infrared should agree for global symmetries, right? This is of a this statement has similar flavor, but it's different because this is an inequality. And the reason is that the 't Hooft anomaly matching works for symmetries that are conserved. Well, here we're talking about a symmetry that is violated along the RG flow. It's only restored at very short distances and at very long distances. So it's generally violated, and this is why we get an inequality. So the interesting thing is that there is a uniform inequality in all the quantum field theories. So now I'll mention some applications regarding the problem of symmetry breaking, which is of course an important problem in quantum field theory. One of the things we would like to know about a given quantum field theory is whether it breaks some global symmetry. So one application is that as long as the short distance physics and the long distance physics are conformal, we can easily see that the flow is irreversible. That's because we've got an inequality, so you cannot go the other way. There cannot be any cycles in the renormalization group evolution, and so on and so forth. Also, mathematically, it's interesting because it gives you a natural foliation of the space of quantum field theories according to their A anomaly. Now, also, I should mention an interesting work by Luty, Polchinski, and Rotazzi, in which they've used similar logic, in fact, to establish that under some conditions, theories cannot be scale invariant. They must be conformal invariant if they're scale invariant. So a theory, if it's a scale invariant theory, must also be a conformal theory. They've used some related considerations. So regarding the problem of symmetry breaking, I'll try to explain why from this inequality alone, in some circumstances, you can prove that the symmetry must be broken, and in some other circumstances, you might be able to prove that the symmetry cannot be broken. So one favorable circumstance where you can prove that the symmetry cannot be broken is that you would assume by contradiction that it is broken, then there will be too many Nambu-Goldstone bosons, and too many Nambu-Goldstone bosons could easily violate this inequality. So you don't want to have too many Nambu-Goldstone bosons, and therefore some theories you can prove cannot break a global symmetry. So that's one interesting application, and there are many examples where you can actually use this inequality to prove that some symmetry cannot be broken. You can also sometimes prove that some symmetries must be broken by using the opposite logic. You assume that the symmetry were not broken, and then you would find too many fermions to match the 't Hooft anomalies. There are many interesting theories in which to match the 't Hooft anomalies you need a ton of fermions. There are many theories that I can mention later if somebody is interested. But many times the solution for the 't Hooft anomaly conditions are so complicated that you need many fermions. And so in these cases, at some point you would violate this inequality, and you would need to give up on the idea that the symmetry is not broken and do break the symmetry. So that's another application. And also there is an interesting quantum field theory interpretation of various phenomena in ADS that have been observed in the past that are associated to this inequality. Okay, I also want to review a bit the developments in 3 dimensions, which I understand have not been covered so much. In 3 dimensions, there was an extremely interesting conjecture just over the last few years by Meyer, Sinha, Jeffries, Klebanov, Pufu, and Savdi, where they found an analog for this inequality that I've just proven, AUV bigger than AIR. So there is an inequality in 3 dimensions where the letter that they use is F. So F is some free energy on a 3-dimensional sphere. And the conjecture was that F of the short distance physics is bigger than F of the long distance physics. There is even a recent claimed proof by Cassini and Huerta using some techniques from information theory for this inequality. Now, one thing that I wanted to say about this measure of degrees of freedom in 3 dimensions is that it's very radically different from 4 dimensions or 2 dimensions, because it also takes into account topological degrees of freedom. So topological degrees of freedom contribute to the measure of degrees of freedom in infrared theories. So when you compare the F of some UV theory and infrared theory, you need to be very careful about taking into account all the topological sectors. And that's extremely interesting. Another thing which is curious about it, and this is where the comments about scale versus conformal are important, is that this quantity F does not seem to be well defined for a free gauge field in 3 dimensions. As I mentioned, a free gauge field in 3 dimensions is dual to a compact scalar. And so it doesn't have a scale current. And for this reason, the free energy on the sphere is not well defined. There is some divergence. So it's somewhat unfortunate that it's not well defined for a free gauge field, because many of the theories that condensed matter theorists, for example, are interested in have free gauge fields in the UV. So it would be nice to look for alternatives, maybe for this F theorem in 3 dimensions, such that it does assign a well-defined value for a free gauge field. Also, there was an interesting paper that came out recently by Klebanov, Nishioka, Pufu, and Savdi, where they've shown that this object in 3 dimensions is not even stationary at fixed points. This is unlike the C and A anomalies in 2 dimensions and 4 dimensions. So that's extremely interesting, because that implies that the function that was constructed using these information theoretic techniques is not a local function. If you have an object that is supposed to decrease, which is not stationary at fixed points, it means that you have to pick the vacuum before you do the computation. And that's against the spirit of conformal perturbation theory and beta functions in the UV. So that's something, again, that would be interesting to understand better. So now I want to describe another set of ideas that they have been working with Alexander Zhiboyedov, who is a student in Princeton University. So we've been looking at other constraints that you can get on conformal field theories by using unitarity, and especially this optical theorem about positivity of various things. So just to remind you, there are already many known inequalities about operator dimensions in conformal field theories. So for example, there are the usual inequalities that follow from the absence of null descendant operators in the conformal algebra. These are the simple unitarity bounds that everybody quotes. Then there is a more sophisticated set of inequalities by Hoffman and Maldacena, where, for example, they can say various things about these anomalies that I mentioned before, A and C. I'll describe another set of inequalities that are in some form very rigorous too, which are, I think, to some extent not known, and I wanted to emphasize them. So let me tell you what we're doing. We take a conformal field theory in any number of dimensions. These theorems that I'm going to quote, they hold true in 3 and 4 dimensions equally well, and in fact probably also in other dimensions. So we take any conformal field theory in any number of dimensions, and we imagine that this theory can be deformed to some gapped phase. And so this can be done in most of the theories, you know. It's not hard. So we deform this theory to some gap theory. So there is some RG flow that takes a conformal field theory to an empty theory. And we call the lightest particle that appears in the spectrum H. So H will be just the notation for the lightest particle that there is in the Hilbert space of this theory. So then the idea is to bombard this lightest particle with virtual states. So virtual photons, virtual gravitons, or any other particle of any other spin you could conceive. And that's what people do in deep inelastic scattering, essentially. The idea of deep inelastic scattering of QCD is exactly that we take the proton or some hadron and we bombard it with the virtual photons. But for the sake of what I'm going to do, it doesn't have to be photons, or there does not have to be a global symmetry. We can bombard particles with gravitons, for example, and that's because the energy momentum tensor exists in every field theory. So it's more natural to try to bombard the lightest particle with gravitons. So to investigate what's going on, you essentially need to compute the amplitude of what's happening when you bombard your state with some virtual graviton. So you need to compute the amplitude for the decay of the states to any final state. And that's given by the usual deep inelastic formalism. Essentially, it boils down to computing some two-point function of energy momentum tensors, but not in the vacuum, rather in a non-trivial state, which is this lightest particle state. So the amplitude for this decay, the amplitude for the dissociation of this lightest particle is given by the imaginary part of this two-point function, not in the vacuum. And this object QV denotes the momentum of the incoming graviton. So now one basically repeats the usual contour arguments using the fact that the total cross-section is positive, and one finds a neat formula saying that Q nu squared, where Q nu is the momentum of the incoming particle, and the power is something that we call tau s. I'll explain what tau s is in a moment. It's given by an integral over something that is manifestly positive definite. These are known in deep inelastic scattering as the deep inelastic sum rules, but we've done it for gravitons, and it holds true in any number of dimensions. It's just a simple kinematical generalization of the usual story. So the only thing that I need to explain is what is this exponent, tau s. So tau s is the difference between the dimension and the spin of the particle. So that's it. It's just it's what's people call the twist. It's the difference between the dimension and the spin. So in 3 dimensions for the energy momentum tensor, tau s is 1, and s is the spin of the corresponding particle. Okay. So the nice thing is that just from this formula, you can prove many bounds on operator dimensions, essentially using the fact that the imaginary part is positive. So we're using unitarity very strongly. And the bounds that you can prove are, first of all, that the anomalous dimensions are a monotonically increasing function. Sorry, the twists are a monotonically increasing function. And more interestingly, the twists are a convex function of the spin. That's a highly non-trivial statement relating operator dimensions in any conformal field theory. So what you prove is that the twist, the spectrum of the operators is such that the twists are a convex function. And the proof, as you've seen, goes through deforming the theory, doing some scattering, and using the optical theorem. So to summarize, one finds that the twist, which is the dimension minus the spin, I remind again, is a monotonic convex function. And that's a completely general result. There was some similar discussion by Nachman in the 70s in the context of QCD, where the motivation was before people knew that QCD is asymptotically free. So people wanted to learn something about high energies by doing scattering experiments in the lab. And so inequalities of this type were tested or proposed in QCD. So let me give you some applications of this convexity so that you'll see that it's a pretty non-trivial constraint. So first of all, you can test that all the anomalous dimensions that people have computed in the context of ADS-CFT, and people have computed many anomalous dimensions of spinning operators. That's one of the hallmarks of ADS-CFT. That works in all the examples, and it predicts many signs that people have verified by brute force calculations and so on. So these inequalities are completely consistent with all the examples. Another lemma that you can prove is about higher spin symmetry, which was discussed a lot in this conference, that if there is a conserved spin 4 current in the theory, then there are infinitely many higher spin currents that must be conserved. That's because the function is convex. So if the first guy is 0, everything must be 0. All the twists must be 0. You can also put interesting bounds on phase transitions in 3 dimensions. For example, the Ising model, which describes boiling water. So you can prove essentially, so let me just jump to the strongest bound that one can prove. By prove, I'll say what I mean by prove. So one can prove that in the Ising model, there will be infinitely many operators of spin S whose anomalous dimension is going to lie between 0.02 and 0.03, essentially. that's extremely strong, and it holds for any spin S. So there are supposed to be infinitely many operators with these dimensions in the Ising model, which suggests that the Ising model has a very good higher spin symmetry, a good approximate higher spin symmetry. Now, to actually prove these bounds, one needs to invoke a little technical assumptions that we may discuss. Okay, so I'll just quickly summarize the open questions. So the question of whether scale invariance implies conformal invariance is not yet known. You could also try to ask about gradient flow between conformal field theories. I mentioned that there are some problems in 3 dimensions that would be nice to resolve. Also in higher dimensions, there are very interesting results that would be nice to investigate further by Elvang and collaborators. And there are many applications of this convexity theorem that I mentioned that could be nice to explore. And of course, finally, it would be nice to compare these results to the Ising model and the critical ON models where these inequalities imply extremely sharp bounds on operator dimensions. And finally, a more general question is whether quantum field theory simplifies at the high spin sector for higher spins. So these inequalities, they suggest that when you go to very high spin, there are very universal things you can say about operator dimensions. So that would be nice to clean up. So I'll just finish with a quote from Polyakov that I think is completely unrelated. So there is this nice quote from Polyakov that when I said that the boiling water may have something to do with deep inelastic scattering, I received a very strange look. And I hope I convinced you that, in fact, this is more prophetic than one might have thought. That's exactly what we've been doing. So, thanks.
We are grateful to our speakers for keeping on their schedule, and we have time for a couple of questions. It's not working.
Maybe I just scream. So you have this integral imaginary part of B prime equal to 0. So I presume that assumes that B prime is a well-defined function with no singularities. Is that easy to see?
To say what? I didn't hear
All right,
almost
maybe.
everything.
Now it works, sorry. You have this formula, integral imaginary part of B prime equal to 0.
Yes.
So I presume that assumes that B prime has no singularities. Is that easy to understand?
So basically when you have a massive theory, you can take 2 limits. One is when the mass goes to infinity, then B becomes the function that is appropriate for the infrared CFT, or you can take the mass to 0. Then B becomes the function that sits in the UV CFT. Okay? And in these 2 limits, it's 0 by word identities of conformal field theories. So in the middle, it's something that interpolates between 0 and 0 in such a way that the total integral is 0 too.
Thank you.